Okay. All right. Well, thank you very much for the kind invitation to speak, and thank you all very much for coming in and standing at the back. I hope to make it worth your while. I should say before I start that I'll be talking about joint work with one of my postdocs who's called Matt Nobleby. And it's also joint with Miguel Rodriguez, who is professor of ECE at UCL, University College London. Now, I'll say a few words about Matt. One, because he's looking for a job. And two, because it's aligned with the theme of the talk. So Matt did his PhD with Behnam Azang, who is a wireless guy at Rice. So he knows all sorts of stuff about wireless. And he had actually done a project with me as a summer intern on wireless, actually on gossip algorithms. And so he wanted to come as a postdoc. And he was looking at the ads for professors in electrical engineering. And what he was observing was that the ads for positions in communications were sort of going like that. And the ads for people in signal processing were sort of going like that. And so we both thought that it would be a good idea if there were something in the general area of signal processing or information processing that would take advantage of what he already knew, which was wireless. And that's really the theme of the talk. So the theme of the talk is that if you're a department and you were thinking that you had to choose between communications and signal processing, you don't. All right, so let me motivate the talk. This is a picture of Toronto. So this is a picture of Jeff Hinton from Toronto. And Jeff Hinton is one of the leaders of deep neural networks. So he's been doing neural networks for a long time. And he's looking especially pleased because he and his two students, their company DNN Research has just been acquired by Google. And so he's looking very pleased. And actually, about a week after this happened, Facebook gobbled up Yann LeCun from NYU. So it was a really good year for academics with small companies in deep convolutional networks. And you know, if you're working for Google, you have access to huge computational resources. In a sense, you know, people think about deep convolutional networks and, you know, whether you need so many layers or whether you don't need so many layers. In a sense, number of layers in Google is sort of like quantum computing in the NSA. I mean, both of them kind of wish that it could be done, and they hope that it's kind of hard. And we, of course, don't work for Google, and so we don't have access to quite the same computational facilities. And so we wanted to ask a different question, which was, you know, are there problems that Jeff couldn't solve even if we gave him unlimited computational resources? And so that's how we gravitated towards this problem. And so here I'm going to be talking about classification. Classification is everywhere. I'll spend most of my time talking about this actually rather small database, so the Yale B database that's got 38 individuals. Each one of them is photographed, I think, in 64 different illuminations. This is the database of handwritten characters, which is a staple in machine learning. And we've also done some work on recognizing textures. Now, what is this? So, I'm going to be talking today really about classifications, but my background is communications. So let's think about the similarities and differences between these two subjects. So, in something like wireless communication, you have an ensemble of signals. You're transmitting them across an unknown wireless channel. And at the receiver, you're trying to figure out which signal you send. So that's a hypothesis testing problem. You're actually not interested in, you want to know whether you sent a 1 or a -1. You don't really care that it arrived as 1.172 something, right? It's really a hypothesis testing problem. In classification, what's known and what's unknown kind of flips. So what's unknown is the signal, what you're trying to classify. You have the freedom to design the channel. You get to design which measurements you make. But it is still, at the end of the day, a hypothesis testing question. And so what we've been interested in is 3 axes. One is how many classes we can tell apart as a function of the number of measurements we make. We're also interested in the question of, as we try and tell more and more things apart, how reliably do we tell them apart? And how does that reliability depend on the number of measurements that we make? So today, I'm going to talk about this paper here, which will appear in the information theory transactions sometime soon. And so this paper is really about this face of the 3 axes. We have worked on this face. If you're a communication theorist, you'll recognize this formulation, because if you're a wireless communication theorist and you've thought about multiple antennas, there's this beautiful work of David Say and his collaborators on the diversity discrimination trade-off. So you have multiple antennas. You can either use them to send more bits, or you can use them to send the bits you send more reliably. And there's a trade-off between one and the other, and he explores that. See here, you have some rate, so the number of classes is increasing exponentially. Your probability of error is also described exponentially. It's got an error exponent. You want to understand how these two things relate. And we've also been doing some recent. Well, I'll talk a little bit about phase transitions, but I'll talk about phase transitions. We've also been doing some recent work about how many measurements you actually really need to learn classes. So trying to use information theory to say something about that's perhaps that can be more optimistic than the standard VC theory. But I won't talk about it. All right, so and so in communications, we have the work of Shannon that says that we can send through various channels at at a rate called the capacity without making errors. And we have this work of David Shea and Li-Zhong Zheng of the diversity multiplexing trade-off. And I'm going to talk about this today, how we might go about that. So let me try and introduce that with an example. So I'm going to talk about the Yale B database here. And this subject is it's a little bit connected to the theme of the place, because it's all about how you represent signals. So there's some beautiful work in the computer vision community about recognizing faces. And it turns out, so the way that the community works, they say, okay, well, what's a face? To a first approximation, it's a convex body. Now, of course, if you've looked in the mirror this morning, and you're not Voldemort, you will notice that you have a nose. So you're not a perfectly convex body. But nevertheless, let's suppose that faces are convex bodies. And what they do is they look at illuminating said convex body. And so they have something called the Lambert model for how convex bodies get illuminated, which is that you imagine a light source is at infinity. So there's like a sphere of illumination. The intensity of a point on the sphere is the intensity of the illumination. And now the intensity of this spot on my face is determined by the normal that goes up. And so you can think of the process of illumination as a mapping from one set of intensities on the sphere to another set. And what people in computer vision discovered was that if they looked at those intensities in the right basis, and the right basis was spherical harmonics, then the entire world, that operator, is basically 20-dimensional, 15 to 20-dimensional, and a face is approximately 9-dimensional. So it's very, very pretty work. Now, you, of course, can object. You can say, well, I know what spherical harmonics are. And when I look at my spherical harmonics, they have some negative entries. Well, they're not illuminations. And they recognize that too. And what they did instead was to produce, perhaps not a basis, but some kind of frame, which was illumination that you could realize. And so they did think about that question. But anyway, the point of telling this story is that I'm going to think about face recognition, and I'm going to translate it to subspace recognition. Right? That's what I'm going to do. All right, so we're trying to figure out who these people are. Now, I'm thinking that I have two individuals here, and this picture is meant to suggest that I'm going to describe each one of them by a subspace. And each realization is some point, and you see, of course, that the points are a little bit off the subspace. Well, if you think about this, I'm going to model my faces by subspaces, but my model's not going to be perfect, right? This capturing the entire world in a 15 to 20-dimensional space, there's still some energy that's left over. And when I make a 9-dimensional model for my face, I'm going to miss some stuff. And so I'm going to want to think about model mismatch as noise. And so I'm going to want to say that however long Jeff works, there's going to be some mismatch between the true model, should there be such a thing, and the model that he's working with. And so that I'm going to want to think about that as noise, because I'm going to want to make the translation to communication theory. How am I going to calculate that? Well, I have a subspace model, I have a realization, I have a projection onto my model, that's the signal, I have a projection onto the residual, that's the noise. I have a signal to noise ratio. What I'm going to want to do is to think about how many things I can classify as a function of that signal to noise ratio. I'm going to be making measurements. What's a measurement? It's a low-dimensional projection. Maybe that's a low-dimensional projection. Maybe that's a lower-dimensional projection. But in any case, I want to tell many people apart. So, and I want to know how many classes can I reliably discriminate. How many features do I need? And I'm going to try and make this duality with wireless. And now, in some sense, starting point is, right, so if you're a wireless guy, you have spent many hours looking at this equation, because H is a Gaussian channel, X is a vector you're putting through there, Z is some noise, and you're trying to figure out X given Y. Okay? Let's think about classification. I'm going to think about my subspace model. So I have some kind of subspace U, and I'm going to excite it with Gaussian noise. Actually, I did faces, but you know, I could do speech as well, because that's how we do speech. We make an LTI model for your vocal tract, and then we excite it with Gaussian noise. So we're doing subspaces excited by Gaussian noise. And so this is the classification problem. And what you observe is suppose I took the transpose of that bottom equation. Okay? When I take the transpose of the bottom equation, I've got this Gaussian vector up front, and then I've got which way does it go? H transpose. And so if you think about this, if I've got a k-dimensional space here, this is like taking k degrees of freedom, k antennas, and sticking them through a Gaussian channel. So this problem of classification, where I'm representing my classes by subspaces, it's really mathematically very similar to the question of pushing subspaces through a Gaussian channel. That's what I wanted to... Very good. All right. So over here, number of code words, number of antennas. So here, coherence interval. This channel here is unknown, and it changes quite rapidly. Actually, usually there's something called non-coherent wireless communication, where this guy changes too fast for you to measure it. Well, it's just not, perhaps not too fast for you to measure it, but it's just not worth you measuring it. So this is a non-coherent wireless channel, and the way that you communicate over non-coherent wireless channels is to send subspaces through them. Because this thing here, it doesn't change the subspace you send. And so over here at this end, you're trying to recognize subspaces. So on this side of the slide is wireless communication for the non-coherent wireless channel. And through the work of David Say and his collaborators, they've established bounds on the capacity. The bounds on the capacity are a function of the signal-to-noise ratio. So the capacity is a power of the signal-to-noise ratio. And, of course, the thing about capacity is that you can't go beyond that. So even if you have a really big computer, you can't beat Shannon. So once I have subspaces, once I have model mismatch, then there becomes a set of things that I can't do. Right? Okay, so over here, we've got classification, number of classes. We have the dimension of the subspace, the number of features, and the noise. So let me try and. So what I'm going to try and give you some feel for is how we take advantage of those connections. Let me not talk to this one. Let me talk to this. So you have to set the problem up so that you can apply the tools that you have. And so here I've got a signal of interest. It's lying on a k-dimensional subspace. So here the mean is 0. We have looked at non-zero means. For simplicity here, I'm just looking at 0 means. I'm going to take these matrix elements to be IID Gaussian, and I've got some set of classes that I'm trying to distinguish. Yeah, so as I said this before, noise power is that. Now, perhaps, so here's a way of setting up the problem. So I have my ambient dimension M. And I am looking at how many things I can tell apart. So I'm interested in rate, so I take the logarithm and divide by M. And so I've got this quantity, and then I've got this is the dimension of so I've got this ensemble, and the length of the ensemble is growing. Perhaps we could have done it some other way, but we did it this way. So you show capacity by looking at a sequence of things that give an answer in the asymptote. So this is how we set up the asymptote. So we're interested in, how many. So this for my face, for my set of faces, this was a 9-dimensional thing. The other one was 15. Okay. So this is what capacity means. We fix these proportions, V and K, and we say that this rate is achievable if you can achieve the rate while driving the probability of misclassification to 0. That's the, okay. Now we're going to, and so if we have more than this number of classes, we have an error probability that we can't slide from under. How do we get upper bounds on capacity? Well, we use mutual information, so this is just an application of Fano's inequality, and I want to get an upper bound on this quantity. Mutual information of the class U given the measurement Y. Oops. No, I'm not going to talk through this. So I wanted to show you this so that you'd see that there was some math there. Didn't necessarily want to go through all the math. What we do is we think about what's the optimal measurement matrix, and we characterize its spectrum in some way. We say we argue that the singular values should all be unity. We're interested in bounding the mutual information, which is this minus that, this minus this. This we approximate by that. This is the probability distribution. And after some mathematics of Wishart distributions, we get to this quantity here. And the important thing about that quantity there is this, because this part disappears, and it's this that enters into the upper bound. So I've swept a bunch of information theory under the rug. I will say that we were hoping at the outset that we could just take this paper by Zheng and Say and just appropriate the results. But we had to work rather harder than we were expecting. How do we go the other way? Well, we go the other way, the way that you usually go the other way in information theory, that is to say by random coding. And so we produce an ensemble that gives this. The Bhattacharya bound on pairwise error. So we do something about pairwise error, and then we use union bounds. Pairwise error, deciding on one subspace rather than the correct subspace. So here you've got your subspaces, and here you've got your measurement matrix. And if you think about this quantity at the top here, this has everything to do with the volume that the two subspaces occupy together. And this, of course, has everything to do with the volume that they occupy separately. And so you can feel that. And in the limit of high SNR, this is determined by the overlap of the dimensions. And so that's why this comes out at the end. And then you use union bound. Okay. And so to summarize the technical content, that this is the no-go region. If you have a certain amount of model mismatch, then you can't, the number of classes you can tell apart can't grow faster than that. Achievability, so there are ensembles of subspaces for which this works. Now, of course, those might not be the ensembles of subspaces that you're really interested in. Can't say anything about that. But that's the I'll say something about how we do on the example. But I wanted to also change gears a little bit because I wanted to say something information theoretic about how you should make measurements. right? And so suppose I have some source. How should I design measurements that are most informative? Or, said another way, how should I make measurements that are maximally informative? And so I'm going to think about how I design a measurement matrix phi. And I want to attack that problem by thinking about what the SVD of this matrix looks like. So of course the SVD has three components. It has a U component and a diagonal component and a V component. Let me just check what's on the next slide. I'm not sure what's on the... Yep. All right. And so I think we're going to do y equals phi x. Yes, we are. So y is phi times x. So the source is going to be over here. So the question is, what's the purpose of V? Right? The purpose of V is to gather as much energy from the source as possible. Well, how are you going to do that? Well, X has a covariance matrix. And so the rows of this matrix here should be the eigenvectors of that covariance matrix, because by making that choice, you maximize the amount of energy that you're taking in. What's the purpose of this guy? So you make this choice for this matrix, and what happens then is you take in energy from the source and you distribute it over these little one-dimensional channels. And each of those one-dimensional channels has a certain signal power. And the function of this guy is to distribute the noise. So the function of this guy is to take high signal energy channels and put them against low noise channels, because that's how you maximize mutual information. So here you can order your eigenvectors decreasing, let's say. So actually I might do it a different way on the next slide, I'm not sure. Let me just check. I didn't say. Okay. So I'll order these so that they're decreasing, and then I'll take the noise eigenvectors and I'll make them increase. And by making the appropriate choices here, I create channels with signal to noise ratios that are going down. Actually, the picture will look at noise to signal, so they'll be going up. All right, and then what's the function of the middle matrix? The function of the middle matrix is to allocate power in the most advantageous way, and that is water filling. So I'll describe that in just a moment. So, so here we've got orthonormal columns, V's got orthonormal columns, and this has got diagonal entries. Good. So I think I motivated this. This should coincide with the eigenvectors of the covariance matrix. This is going to mess with the noise, and the diagonal elements are going to be chosen to water fill. And I've got a picture on the next slide which explains how water filling happens. You have a certain amount of power that you want to allocate to the channels, and what you do is this. So here what I've done is I've arranged the channels. They have this fraction here is decreasing. So this is the noise power, that's the signal power. So as I go down here, my channels are getting better and better. And I think of power as water, and I put in water, and I see where it finds its level. And this height tells me how much power I invest in the appropriate channel. So I'm not going to, don't think I'm going to talk about that. All right. Yeah, so this is the information theoretic optimal sensing matrix. We have, actually I don't have slides for that today, but we have thought about, I mean, our proof of concept for this was to take the MNIST database and to, which is the one with the handwritten digits, and to ask the question, if you could only make one measurement, what measurement would that be? If you could make 3, 4 measurements, what would they be? And we have an ICML paper where I mean, the machine learning community has sort of beaten this database to death, but it's still possible to get small improvement. We got a small improvement, so it's actually, so now I forgot to say that, and this I'm slightly embarrassed by, because before I was at Duke, I was 6 years at Princeton. And this theory of how mutual information connects to the MMSE is something that was discovered, if you like, by Sergio Verdu. There's a beautiful paper by his student at the time, Dongning Guo, and Sergio and Shlomo Shammai, which explains it. And what I'm kind of embarrassed about is that I never talked to him about it when I was at Princeton. And since I've got to Duke, I've actually used it in 4 or 5 papers. So but this is I mean, it's a really beautiful theory. And I mean, Sergio did it first of all for scalar Gaussians, then he did it for vector Gaussians, and then he did it for arbitrary distributions. Arbitrary distributions is a bit more complicated. It's not simple water filling. It's something called mercury water filling, where what Sergio does is, if you look at this picture here, so in this picture there's the signal and there's water. In mercury water filling, there's signal, a layer of mercury, and a layer of water. And it's mercury water filling because mercury sinks. And the layer of mercury is really about the difference between your distribution and the Gaussian distribution. That's how that works. Anyway, so that's a beautiful... All right, so let me conclude by going back to faces. So these are the references for the computer vision folk. So here we are. We're sitting in this 15-dimension. So I mean, it's fortunate that the numbers work out to be small. So we're living in this 15 to 20-dimensional space. We've got a 9-dimensional subspace of interest, which is the face. And what we'd like to do is to do a little experiment that that perhaps suggests that we do indeed have a phase change associated with capacity. All right, so it's a modest data set. For each subject, we use half of the images for training. our classifier is just a maximum likelihood subspace classifier. What happens? Well, that's what happens. So even when we have all the information, we don't actually do better than that. So that's how we defined success. We compare to when we compare to the predicted capacity. This is what we would that's where we would expect to see the phase transition, and we'd expect to see it sort of exist over 2 to 3 measurements, and instead it's rather wider. But still, I mean, we were happy to see this kind of threshold performance. Why is it 5 to 10 rather than 2 to 3? Well, there's a lot of, I mean, the subspace model is not exact. There's a kind of power law distribution in the amount of energy you catch and the amount of energy you lose. But I think that it is directionally correct. And what's the conclusion? What I think, what Matt is certainly hoping, is that wireless expertise is applicable to machine learning, that there is a notion of capacity. So if you accept that there's going to be some degree of model mismatch, then you have to admit some notion of capacity. Some things that we didn't talk about, and that's the paper at the bottom. So thank you for your attention, and be happy to. Yeah. Okay, so the question is that there's some recent work in the information theory community on finite rate capacity. So this is work by Yuri Polyansky and Victoria Costina, so Sergio Badou's students. And the answer is yes, certainly. We didn't do that, but it's certainly something that we have in the back of our minds, yes. Bitte? Yeah. I don't know. It's a very good question. It's, yeah, I don't know the answer to that. Yeah. Yeah. Yep. Too many thoughts. I don't know. It's I mean, I think, all right, so let me give a philosophical answer. I mean, first of all, I mean, I think that there isn't a more, in some sense, there isn't a more interesting question than deep learning. In fact, I mean, one of the reasons that we did this was, I mean, I have great affection for the information theory community, and so, but sometimes the information theory community takes the point of view that it works on the problems where they like the methods, And if the problems haven't caught up with the methods that we like, well, then that's too bad for the problems. And so what we wanted to do was to do something which suggested to people in information theory that they could say something about deep learning. And so what we hoped to do was to get more people thinking about that area. I mean, I do think that the information theory community is fantastic at thinking about graph-based decoding algorithms. Right? So things like LDPC codes, things like spatial coupling. Right? They are incredibly clever and they have really deep algorithms. And I think that they have something to offer to the people that design deep convolutional nets, right? What is the purpose of a deep convolutional net? You know, what are you calculating? What metrics are you calculating? What messages are you passing? What's the geometry of that calculation that you're doing? Right? Are you doing some kind of contraction in some geometry? I mean, I think these are all fantastic questions. I think it's a hugely interesting problem. It's a really important problem. And so, you know, what we're trying to do in this talk is to tempt people in, sort of to peel back the curtain and say, there's something really interesting behind this curtain. Yeah. Well, I mean, the erasure channel is always a good surrogate for more complicated things. But I think things like density estimation, I think things like approximate message passing, these are all, I mean, there's something in each of those, I think.